In this lesson, we will discuss proportional reasoning. In science, we often want to know relationships between variables. For example, we may want to know the relationship between the distance of a star and how bright it appears. Or, in everyday experience, for example, you may want to know the relationship between sunlight and the growth of a tomato plant. Again, a key characteristic of science is that we study relationships between variables. Relationships between variables are expressed as equations. For example, the following expression means that y is proportional to x. Now, there are many possible equations that can satisfy this proportionality. For example, y equals 5x, or y equals 10x, or y equals minus 3x are all examples of y being proportional to x. Let's study what this means in a little more detail. If y is proportional to x, then if we double the value of the variable x, then the value of y doubles. For example, let's let the height of this purple column be represented by the variable x. The height of the orange column is represented by the variable y. Suppose then, if this proportionality is true, if we double the height of x, how large will y be? Well, it will double because they are proportional. If you imagine that in my earlier simple example of sunlight being proportional to the growth or maybe the number of tomatoes produced by a tomato plant, suppose you found that the minutes of sunlight each day was proportional to the number of tomatoes produced on a tomato plant. Then, if you were to double the minutes of sunlight for that plant, the number of tomatoes produced would also double. Now, that may not be true, but it's an example of a relationship. Perhaps a better relationship is the circumference of a circle. The circumference of a circle is proportional to its radius. If you double the radius of a circle, then its circumference also doubles. Let's use an example from astronomy. One of the most important laws in astronomy is Hubble's law. It describes the expansion of the universe. Hubble found that galaxies are receding, meaning that they move away from us, with a speed that is proportional to the distance from us to the galaxy. We call this the recessional speed. Written as a proportion, the recessional speed of a galaxy is proportional to its distance from us. Suppose then that a certain galaxy, galaxy A, is a certain distance, d sub A, from Earth, and it has a recessional speed of s sub A. Another galaxy, galaxy B, is twice as far as galaxy A. How fast is it moving away from us? The answer is that if or since the recessional speed is proportional to distance, then galaxy B should be moving at twice the speed as galaxy A. The reason is that the speed of a galaxy is proportional to its distance from us. If we double the distance, we double the speed. Since galaxy B is twice as far as galaxy A, then it's moving twice as fast. Let's look at another example. Y is proportional to x squared. In this case, if you double x, that doubling gets squared. Well, what is 2 squared? It's 4. So doubling x results in x squared increasing by 4, which means that y increases by 4. So doubling x results in 4 times the value of y. When x is doubled, y increases by a factor of 4. Okay, suppose then that you increase x by a factor of 3. Again, y is proportional to x squared. By what factor would y increase? Remember, if we multiply x by 3, that 3 gets squared. And 3 squared is 9. So tripling x would increase x squared by a factor of 9. And since y is proportional to x squared, then y increases by a factor of 9. Okay, why don't you take a moment to practice this idea? Again, using the same proportionality, y is proportional to x squared. If you increase x by a factor of 4, by what factor will y increase? If you have not answered yet, you may pause the video, and I will give you the answer now. Since y is proportional to x squared, 4 times x results in an increase of 4 squared for x squared. In other words, multiplying by x by 4 increases x squared by 16. The 4 gets squared, meaning that y increases by a factor of 16. Let's look at an example in astronomy. The area of a sphere is A equals 4 pi times the radius of the sphere squared. Suppose that a star has a certain radius r. Suppose then that that star expands so that its radius is twice as big, 2r. By what factor does the area of the star increase? In other words, if you double its radius, by what factor does its area increase? The answer is 4. Since the area is proportional to radius squared, if you double r, that factor of 2 gets squared, giving you a factor of 4. So doubling the radius of a star increases its area by a factor of 4. Another way to say it is if you had one ball of a certain radius, then a second ball of twice the radius will have 4 times the area of the first ball. Here's another example that we'll encounter in astronomy. Y is proportional to x to the 4th. If we double x, how much does y increase? Well, doubling x means that 2 is increased by a factor, an exponent of 4. So the factor is 2 to the 4th power, or 16. So this means that doubling x results in an increase in y of a factor of 16. Here's another example that we encounter in astronomy. Y is proportional to 1 over x squared. In this case, the x is in the denominator. So when we double x, we will get a factor of 1 over 2x squared, resulting in a factor of 1 over 2 squared, which is 1/4. So increasing x by a factor of 2 results in y decreasing, getting smaller, by a factor of 1/4. Actually, we call this an inverse square proportionality, meaning that if y is proportional to 1 over x squared, as the denominator gets bigger, if x is made bigger, y becomes smaller. Let's look at this proportionality applied in astronomy. The brightness of a star depends on 1 over the distance to the star squared. Now this makes sense. If you imagine that I have a light bulb very near to you, it will look very bright. If I take that light bulb and I take the same light bulb but just move it further from you, it will look dimmer. And the actual brightness as measured will depend on 1 over the distance to that bulb squared. We can write this as a proportion. Brightness is proportional to 1 over distance squared. Suppose that star A and star B are identical stars. If star B is twice as far as star A, what will be its apparent brightness compared to star A, as measured by us here on Earth? In other words, take two identical stars and one is 2 times further than the other. What will be the brightness of the further star compared to the closer star? Well, first of all, it'll be dimmer. And so the brightness since it varies as 1 over the distance squared. Doubling the distance means that the brightness decreases by a factor of 1 over 2 squared, or 1 over 4, 1/4. So star B, since it is twice as far as star A, will be 1/4 as bright. This is a very conceptual kind of question, even though you use math to answer it. And understanding proportionalities and relationships between variables is very important in science. Just to summarize, we've looked at 4 proportionalities. Y is proportional to x, y is proportional to x squared, y is proportional to x to the 4th, and y is proportional to 1 over x squared. You should know how varying x will affect y. In other words, if I multiply x by some factor, by what factor does y change, whether it increases or decreases?